Hello, everyone. I'm Pan Hu. From this week, I will deliver lectures for the second half of this pavement materials and design unit. I'm going to talk about asphalt mix design, design of the flexible and rigid pavement, and finally, the pavement maintenance. Today's lecture is about asphalt mix design. Now let's have a look at two important types of pavement structure: flexible pavement and rigid pavement. Flexible pavement is normally composed of a varying surface, a base, and a subbase and subgrade. The varying surface of the top layer is in direct contact with the traffic. It is normally made of asphalt concrete or bituminous concrete. Asphalt mix design is the design of the asphalt concrete varying course. It is specifically designed to resist abrasion from traffic and to minimize the entry of water. The asphalt varying surface must also have suitable surface friction properties for adequate skid resistance. Rigid pavement is normally composed of cement concrete, subbase, and subgrade. We will focus on the asphalt mix design of the flexible pavement in this lecture and discuss rigid pavement in the following lectures. For asphalt mix design, normally the guidelines and specifications need to be followed. In Australia, the asphalt mix design is based on the procedures contained in the guidelines in Australian Asphalt and Pavement Association, AAPA, and Australian Road Research Board, ARRB. These guidelines aid to promote good practice in the process of asphalt mix design and improved understanding of the selection of design procedures for particular application. In basic terms, asphalt is a mixture of coarse and fine aggregates, the mineral filler, and bituminous binder. The asphalt mix design involves the selection of aggregate type and grading, the binder type, and binder content. The aim is to optimize the engineering properties of the asphalt to achieve the required engineering behavior. The basic requirements for asphalt are adequate load carrying capacity or resistance to deformation, and durability. Specific requirements vary considerably with traffic loading levels, operating environment, and underlying base conditions. For asphalt mix design, certain performance-based design criteria must be met. Here we have key performance indicators: deformation resistance, the fatigue resistance, durability, and moisture sensitivity, which will be discussed in details in the next slide. There are three levels of tests. Level 1 tests are for checking the volumetric properties. Level 2 tests are for obtaining mechanical properties, while level 3 tests are verification tests. If these key performance indicators could not be met, then different types of pavement distress would occur, like rotting, the fatigue cracking, the raveling, and stripping. Now let's go back to see these performance indicators and corresponding distress. If there's no sufficient deformation resistance, then rotting would occur, which shows the surface depression in the wheel path. One of the main reasons of rotting is improper mix design or manufacture. For example, excessively high asphalt content, excessive inner filler, or insufficient amount of angular aggregate particles. There is also fatigue cracking due to insufficient fatigue resistance. By the way, the fatigue is the weakening of a material caused by cyclic loading that results in progressive and localized structural damage and the growth of cracks The fatigue behavior of an asphalt layer depends not only on the properties of the mix, but also on the structural properties of the underlying pavement layers, the traffic and climate conditions. Durability and moisture sensitivity are another two performance indicators, and the corresponding issues are raveling and stripping of the varying surface. Raveling is the progressive disintegration of a pavement surface through loss of both binder and aggregate. Asphalt stripping is essentially asphalt raveling in reverse. So instead of the surface coming apart, disintegrating and exposing the lower layers of the asphalt fall apart first and damage the upper layers. So we need to optimize the asphalt mix design and avoid this pavement distress. Asphalt mix design involves the following 9 steps. Initially, we need to select the mix type, then the component materials. Select of mix type for particular performance conditions will set the parameters for aggregate grading, the binder type, volumetric properties, and the general performance characteristics of the mix. Afterwards is combining aggregates to meet target grading. Then select trial binder content and range, and mix condition and compact asphalt mix to simulate field condition. The 6th step is to determine the volumetric properties of the compacted mix and select design bitumen content. Step 2 to 6 belongs to level 1 testing. Step 7 is the mechanical testing or level 2 testing. Step 8 is the verification test or level 3 test to check the air voids or wheel tracking results of the asphalt samples. Finally, step 9 is the selection of job mix. The job mix will nominate the type and source of components, target grading, the binder content, and volumetric properties of the mix. This is the flow chart of the 3 levels of the ROSE mix design procedure. We will go through the details of this design process in the following part of this lecture. Now let's have a look at the details of each slide. In basic terms, asphalt is a mixture of coarse and fine aggregates, the filler, and bituminous binder. There are mainly 4 asphalt types: dense graded, open graded, stone mastic, and fine gap graded. The most common type of asphalt is a dense graded mixture. This is the focus of our lecture. A dense graded asphalt mix has a continuous distribution of aggregate particle size and filler and a low design air void content, generally in the range of 3 to 7%. The open graded asphalt is characterized by a large proportion of coarse aggregates and only small amounts of fine aggregate and filler. Due to large voids, its usage can lead to reduced noise and reduced surface water and spraying. The stone mastic asphalt is also a gap graded mix, but with a high proportion of coarse aggregate, providing an interlocking stone-on-stone skeleton that resists permanent deformation. Generally, it has high durability and high rot resistance. It is primarily used for heavy traffic roads, but it can be used for all types of pavement. A fine gap graded asphalt mix is a dense and low air void mix, but with intermediate size fractions replaced by finer fractions. It is the durable mix for low traffic situations, such as residential streets, and other light-duty applications. The dense graded asphalt is most popular used in the field. It could be used for strengthening or correcting irregularities, or even fixing an existing pavement. Constructing a new pavement, improving the surface properties and the working surface of existing and new pavements. So surely this dense graded asphalt has multiple applications, and it is the main focus of our unit. The other mixed types like open graded, stone mastic, and fine gap graded asphalt are mainly used for the pavement to meet any special requirement. Step 2 is to select component materials. The principal factors influencing the performance characteristics of asphalt mixes are the skeleton and quality of components and the volumetric properties of the mix, like nominal size, the grading, the binder content, and void relationships. The selection for binder depends on the environmental conditions, such as temperature and traffic, and property requirement of the asphalt. The binders for asphalt manufacture mainly contain two groups: the conventional and modified bitumen binders. There are two types of modified bitumen binders: the multi-grade binder and polymer modified binder. Now let's look at the details of each type of the binder. The most commonly used bituminous binders in Australia is the conventional bitumen. According to its viscosity at 60 degrees, the conventional bitumen could be divided into three major grades: class 170, class 320, and class 600. By the way, the viscosity of the bitumen is a measure of its resistance to deformation at a given rate. The softer grade, like class 170, is good at resisting fatigue and cracking due to its flexibility and durability. So it is typically used for light traffic and in cool climates. The harder grade, like class 600, is good at resisting rotting or deformation of the pavement. So it is generally used for pavement with heavy duty. The medium grade class 320 has good resistance to rotting while maintaining flexibility and durability. So it is the most versatile and commonly used type of binder. Now let's look at the modified bitumen binder. Compared to standard bitumen grades, the multi-grade bitumen is less susceptible to temperature change, so it can provide improved deformation resistance at high surface temperature, while retaining the desired level of flexibility at low temperature. The polymer modified binder is adding the polymer to increase binder toughness and elasticity. Toughness is the ability of a material to absorb energy and plastically deform without fracturing. The polymer modified binders are normally used to enhance the properties of bituminous binders to improve performance on heavily trafficked pavement surfaces or provide greater flexibility. Its good performance includes improved flexibility, the cohesion, and resistance to deformation of asphalt mix at high temperature. According to different application purpose and different climate in the area, we can choose different type of binder from class 170 to class 320 and either multi-grade binder or polymer modified binder. For example, if it is intended to be used for residential driveways and in moderate climate, then we need to use C70, C170, or C320 as binder material. We already learned the selection of binder in step 2. For step 2, we also need to select the aggregates. The nominal size of the aggregate could be determined as a function of the layer thickness, or the layer thickness could be selected on the basis of the nominal size required for a particular application. A guide to selection of layer thickness and nominal size is shown in the table here. For example, if the nominal size of the dense graded asphalt mix is 40 millimeter, then the layer thickness has to be greater than 100 millimeter. Step 3 is to combine aggregates to meet target grading. The target grading has to meet the grading envelope requirement. In general, the grading envelope is the particle size distribution of the aggregate. This table is the percentage of passing. Each side is sieve size for different nominal size of the aggregate, the AC10 to AC40 on this table represent nominal size, and these values in the tables are the percentage passing sieve size in terms of mass. When we plot the data in log scale, where the horizontal axis is the sieve size in log scale, and the vertical axis is the percentage of passing. Here is how the grading envelope looks like. According to the previous table, for AC14, we could plot the upper bound and lower bound curve, and normally the target grading falls in between them. A target grading may also be chosen from empirical formula. Well, most engineers will work from standard grading curves, such as those given in previous table. It is possible to work from a design formula, such as that of Fuller and Thompson equation. So P equals 100 times D divided by capital D to the power of N. So in this formula, the capital P is the total percentage passing a given size. If we know the size of the sieve D, the maximum particle size capital D and the exponent could be taken as the value in between 0.4 and 0.7 to stand for boundary values. Then the percentage for mass of aggregate passing a given sieve capital P could be calculated. This equation produces the maximum particle density when we take this N as 0.5. In this unit, we have the opportunity to conduct lab testing on pavement materials. If you have done the lab testing, then here is the lab sheet you need to fill in. You could use the Fuller and Thompson formula to calculate the target grading, and then work out the values for all three samples with bitumen content of 4% to 6%. We will practice one example by the end of this lecture. We could also work out the proportion of combined coarse aggregate PC, the proportion of combined fine aggregate PF, proportion of filler PFill, and bitumen content capital B. Be aware that PC is for coarse aggregate with particle size equal or greater than 4.75 millimeter. PF is for fine aggregate with size less than 4.75 millimeter, but equal or greater than 75 micrometer. And PFill is for filler size less than 75 micrometer. For example, for sample 1, the bitumen could be calculated as the total mass 1,200 grams times 4%, and we get the value of 48 grams. Next step is to select a trial binder content on the basis of past experience, or to make sure to meet the requirement of minimum binder film index of 7.5 micrometer or greater. The binder film index is a measure of the average binder film on the aggregate particles, excluding any binder which might be absorbed by the aggregate. This allows the mix to have adequate durability and fatigue resistance. Normally, the binder film index gives the minimum binder content, and the trial binder content will normally be 0.5% higher than this. By using the trial bitumen content and the trial 1 plus and minus 0.5% and 1%, we're able to get a range of bitumen contents. Once the trial binder content is chosen, we start to mix and then condition and compact the asphalt mix in step 5. We need to ensure the sample prepared in the lab have properties as close as possible to asphalt placed in the road, and this is an important aim of asphalt mix design procedure. As discussed before, the class 320 bitumen is commonly used in asphalt for medium and heavily trafficked mixes, so we will choose it for mixing. The mixing is conducted for a range of bitumen content and normally in between 4% and 6%. The aggregate and binder are heated in an oven and mixed at 150 degrees. The mix is then transferred to an oven and conditioned under 150 degrees for 1 hour. It simulates the hardening of the binder during manufacture, placing of the mix, and initial service period. In such case, the prepared sample could reflect the real behavior of the filled pavement. For the compaction of the sample, the gyratory compactor is used to compact the samples for the required number of cycles. The compactor could produce 100 millimeter and 150 millimeter diameter cylindrical asphalt samples of specified density. The applied shear force to the asphalt mix is similar to that from the roller during the construction of the road. During compaction, the mold is rotated relative to its vertical axis shown here through a constant gyration angle during the compaction process. So this is the gyratory or gyration angle here. So the vertical compressive pressure is applied to the asphalt sample within the mold. The produced samples have mixed characteristics very close to those found in the filled pavement. This is the data sheet for gyratory compaction tests. This enables a selection of different compaction levels to match service conditions and simulation of long-term heavy traffic by compaction to refusal density. The refusal density is also the final density of the sample. Step 6 is to determine the volumetric properties to select design bitumen content. Let's have a look at the volumetric relationship. In the diagram, the HMA stands for hot mix asphalt. The bigger particles are the aggregate. Some of the asphalt are absorbed into the aggregate. The VMA or voids in the mineral aggregate are occupied by the air voids and effective asphalt binder. From the right volume diagram, we can also see that the asphalt binder is composed of the effective asphalt binder and absorbed asphalt binder. If the relationship is expressed in terms of mass or volume, here's how the composition looks like. If we look at mass, normally the air voids have no weight. The binder is expressed as capital B, and BE stands for the effective binder, and small b for absorbed binder. From volume point of view, AV is the volume of air voids, and VB is the effective volume of the bitumen. The sum of them is called VMA, the voids in mineral aggregate. Typical values of VMA in dense mixes can be 13% to 20%, depending on the nominal size of the mix. Finally, Vg is the volume of the aggregate, including the absorbed binder. I would strongly suggest you to pay more attention to these definitions and relationships, as you'll need to use them for some calculations. So based on previous figure, we have the following useful volumetric relationships for air void content AV, voids in mineral aggregate VMA, and voids filled with binder VFB. Among these formulas, the rho max is the maximum density of asphalt in tons per cubic meter. The rho bulk is the bulk density of asphalt in tons per cubic meter. And capital B is the proportion by mass of binder in total mix. Rho B is the density of binder in tons per cubic meter. And finally, rho A is the bulk density of the combined mineral aggregates in tons per cubic meter. This is the follow-up of previous slide. The bulk density of the combined mineral aggregates could be calculated using this formula. The physical meaning of each symbol is shown below. The BE is the proportion by mass of the effective binder as percentage, which can be obtained from the following equation. The small b is the proportion by mass of the binder absorbed as percentage. It could be calculated from the bottom equation. After you conduct the lab testing, you should be able to obtain the measured values for datasheet C.1 and D.1. The maximum density of asphalt or rho max could be obtained by the combination of the table and the formula below. We are the M1 to M5 are the testing measurements. Similarly, the bulk density of asphalt could be calculated based on the datasheet D1 and the formula below. Where M1 to M3 are the testing measurements in the table, and rho W is the density of water in terms of grams per cubic centimeter. After we conducted tests on the samples of 5 different bitumen content, we are able to get the relationship plot of this air voids density and VMA, or voids in mineral aggregate of the compacted samples and bitumen content. They could be used to evaluate whether the mix meets any required specifications. If the mix has the required air void content, then the binder content could be determined from the plot. For example, if the air void of 5% is required, then according to the first figure, the design bitumen content is chosen as 4.8%. Also, we could check the sensitivity of the asphalt mix in terms of these parameters to binder content from these figures. For example, if the bitumen content was increased from 4.5% to 5%, how the air voids, the density, and VMA change accordingly. The step 7 is the mechanical testing to get a series of properties such as the film index, resilient, modulus, creep. There are two operational tests: moisture susceptibility and beam fatigue resistance. These tests are only for medium to very heavily trafficked road. Ideally, the mechanical properties of asphalt in situ are required for pavement design purposes. Reproduction of in situ stress conditions in the lab is difficult, so these simplified tests are introduced to indicate certain aspects of the in situ behavior. The relationships of these properties with the binder content are shown in these figures. So we can see that the testing is performed at a single trial binder content 5%. If the requirement from the specification or guideline is not met, we could plus or minus the trial binder content by 0.5% or 1% and prepare a new mix until the requirement is properly met. In previous slides, we discussed level 1 and level 2 testing. Level 3 testing is the testing for verification. It is only required for heavily trafficked road or where extra reliability in terms of routing performance is required. It has two parts: the check of the air voids using a gyratory compactor at 250 cycles and view tracking of the asphalt slabs. Let's look at air voids verification test first. The air voids content of a mix affects the stability and durability. Experiences indicate that asphalt mixes with air void content less than 2 to 3% are likely to be unstable and prone to rotting. This is because the binder almost totally fills the void spaces and reduces aggregate particle interlock and friction. The specification requires the mix, which has a design air void content of 5%, must have greater or equal to 3% voids at 250 cycles. With a mix, a mix with design voids of 4% would need to have greater or equal to 2% voids at 250 cycles. We could take measurement, work out the air void at 250 cycles and check if it meets the above requirement. This air void check is normally done during the level 1 testing. The view tracking test is the asphalt slab repeatedly traversed by a loaded wheel to correlate to road performance as shown here. It is used to measure the deformation resistance and widely accepted in a number of countries. For wheel tracking, normally a 300 millimeter square slab with 50 millimeter deep or 75 millimeter deep is made from the asphalt mix. The corresponding air voids of the slabs must be 5 plus 0.5% to get a characteristic value. The test is normally carried out at 60 degrees using a wheel of 50 millimeter width and 200 millimeter diameter with top load generates pressure of 700 kPa. The results are expressed in terms of wheel tracking rate or final tracking depth. You can watch a wheel tracking test demonstration through the link below. The wheel tracking test is stopped either when 10,000 passes have been completed or the tracking depth is greater than 15 millimeter. For the parameter of wheel tracking rate, it is calculated as the change in tracking depth with the number of passes over the range of 4,000 to 10,000 passes. The result could be converted and is priced as the final tracking depth after 10,000 passes. Although the tracking range is commonly used overseas, it is not considered. The tracking depth after 10,000 passes is a more appropriate parameter to indicate the asphalt performance. Some typical tracking depths for laboratory prepared asphalt samples are shown in the table below. So if the tracking depth is 3 millimeter, it indicates superior performance. Otherwise, 14 millimeter indicates the low performance. For aggregate grading calculation, we could have a better understanding of the calculation process from the example in tutorial 6. In this table, we have 3 samples with bitumen content of 4%, 5%, and 6%. The sample weight is 1,200 grams. So for 4% bitumen content, the weight of bitumen is 48 grams, and the total weight of aggregate is 1,200 minus 48 equal to 1,152 grams. The upper and lower bound grading LLOS values are shown in the last 2 columns. The calculated grading ought to be bounded by these values. The first column is the sieve size, and the second column is the percentage of the weight retained based on grading target from Fuller and Thompson formula. Normally, the first 2 columns and the last 2 columns are given. For sample 1, firstly, we need to work out the mass retained. So using 1,200 grams times 96% or 0.96 times the values in column 2. The mass passing is the mass of the aggregate minus the retained mass from each sieve. And finally, the grading is calculated using the passing mass divided by the mass of the aggregate, 1,152 grams. We could do the same way and complete the table for different bitumen content. Next, according to the threshold of PC, PF, and PFill, we could work out the weight of coarse aggregate, fine aggregate, and filler. The percentage of bitumen is 4%, so the weight is 48 grams. If we take the PC for example, it corresponds to the retained weight for sieve size equal or greater than 4.75 millimeter. So if we go back to the previous slide, the total weight of aggregate is 1,152 grams, and the mass passing the sieve size of 4.75 millimeters sieve is 599.04 grams. So the weight of coarse aggregate is 552.96 grams. If we divide this value by the total weight of 1,200 grams, we get the PC value of 46.08 in percentage. Similarly, we could work out the PF and PFill. For the red table, we could make full use of the formulas we learned in this lecture to get all these values. All right, a summary of this lecture. The asphalt mix design process has 3 levels and 9 design steps. Level 1 testing is to obtain the volumetric properties. The level 2 testing is the mechanical testing, while level 3 testing is the verification testing. We learned how to calculate the aggregate gradation and the percentage of coarse aggregates, fine aggregates, and filler for a specific bitumen content. We also learned how to use the formulas to calculate the volumetric properties of the asphalt mix, such as AV, VMV, VFV, and a few other parameters. Finally, according to the specification or requirement, like design air void content, we could determine the design bitumen content from the plots of testing results. That's the end of the lecture today. Thank you for your attention, and I hope you guys have a wonderful day. I'll see you next time.